Okay, impulse. As you know, momentum is equal to, momentum P is equal to mass times velocity. That's something you're familiar with. Now, how do you change the momentum of an object? Well, in order to change the momentum, it's much easier to change the velocity than changing the mass. It's not that you can't change the mass, it's just you don't typically see those problems um, without calculus, and we're not going to do that. So basically, if you want to change the momentum, you got to change the velocity. So changing the velocity requires a net force. As you know, net force is mass times acceleration. But the acceleration is a change in velocity over a change in time. Let's do a little bit of substitution here. So the net force acting on an object is m times delta v over delta t. So far so good. I basically just took the delta v over delta t, put it in for a, and this is what we get. Now, that's not as useful as other things. So let's move down. In other words, the net force times the time multiplied by the time is equal to the mass times the change in velocity. Now, this should be somewhat familiar. I have no doubt that you saw that last year at some point um, first semester. The net force multiplied by the time is equal to the mass times the change in velocity. Now, as you know, let's back it up a little bit here. As you know, if momentum is mass times velocity, then a change in momentum is mass times a change in velocity. That's your change in momentum. But impulse is a change in momentum. That's F times delta T. Now I'm kind of moving between net force and average force. Um, really, if your motion is changing, it's because there's a net force, but we're actually just going to call it average force here. So change in momentum, mass times a change in velocity. Impulse is the average force multiplied by the time. Conceptually, if you think about this, if you apply a force for a certain amount of time, your velocity changes because there's an acceleration. The longer you apply that force, the more time your velocity has to change. And so you get a greater change in momentum because you apply the same force for a longer period of time. Okay, conceptual look at it. All right, let's do an example problem. A bullet with a mass of 0.02 kilograms hits a block of wood. Let's assume that the block of wood is stationary and fixed and isn't going to move on its own at a speed of 320 meters per second and comes to a stop 0.01 seconds later. Calculate the impulse and the average force applied. Now, um, let's just take this one step at a time. Maybe write down what we know. Mass is 0.02 kilograms. V1 is 320 meters per second. V2, as you hopefully are aware, is 0. Let's see, time is 0.01 seconds. Now, impulse, by definition, is a change in momentum. Now, we don't need the force in order to change the impulse as long as we know how much momentum we started with. So 0.02 times 320. Well, let's see if I can move some decimal places here. I'll get the calculator out here in a second, but let's just do this the cheap way. So move the decimal over 2, move the decimal over 2. 3.2 times 2 is 6.4. So 6.4 kigums. Let's just verify the math here. 0.02 times 320, 6.4, as expected. Okay. this is how much momentum we had at the beginning, at the end, 0. And we know that because it's not moving anymore. So this is how much momentum was lost, otherwise known as impulse. Now, let's come down to the average force. Well, we know that impulse is equal to the average force times how long you apply that force. 6.4 kilograms is equal to what we're looking for times 0.01. All right, well, this one shouldn't be too bad. I'm just going to move decimal place over 2, move the decimal place over here. The average force is equal to 640 newtons, and I think I need to extend the page here. All right, so far so good. So impulse is the change in momentum. If it had momentum at the beginning and 0 at the end, that difference or that total amount of momentum at the beginning is what the impulse is. If you know the impulse, then you can calculate the amount of force or the time, depending on what other information is given to you. All right, getting closer. Now, graphical representation of impulse. If you apply a constant force, then the impulse is equal to force times time. Pretty straightforward. But if you think about it, that is really just the area under the graph. It's a rectangle base times height, and there's the area. So 20 times 6 gives me 120 kilograms. That's your impulse force times time. It's the area under this graph. Fairly straightforward. You guys should be aware that the area under the graph usually has some kind of physical significance. What's different, and this is the thing that you want to realize, is that in energy we had force and distance. Now we have force and time for momentum. That's something you really should keep in the back of your mind, because if I give you a force and something graph, you have to recognize whether that graph tells you about momentum or energy, and the time and distance are the two things that you need to know. Okay, so if I give you a force versus time, it's momentum. Force and displacement, it is energy. All right, moving on. Let's see if I can click that. There you go. Now, if the force changes, it's often easier to calculate areas instead of trying to determine the average force. For example, this bad boy right here. We've got a force that increases and decreases, and it takes about 6 seconds to do all of that. Okay, now, this triangle is really nice. We got a base of 6, a height of 20, and as you know, 1/2 base times height gives you 1/2 6 times 20, and hopefully you guys figure out that that's 60 kilograms. I don't think I'm even going to get the calculator out for that one because, you know. All right, so if you are given a force versus time graph, doesn't matter what the shape is, you know, we're going to give you something that's either linear or, you know, well, it's either going to be rectangles or triangles or some combination thereof. We're not going to give you curves because that's just annoying, but this is the idea. All right, I think we got that. Oh, I gotta get the thing. Sorry, I'm just mumbling to myself now until I find the pause button here.